Hello everyone, hope you are doing great. Okay, so let's go through electrochemical cell MCQ. All right, there are 14 of them. Okay, let's get started. All right, you can see from this question there's a voltaic pile, right? So this is the first modern electric battery. So the voltaic above has 4 pairs of copper silver discs. So let's highlight 4 pairs of copper silver discs. So you have actually like 4 little batteries, and you have 2 pairs of copper zinc discs. So you have another 2 batteries, right? So let's check out this copper silver disc, right? So these are the 2 half cell. Can you see that? So that constitute one little tiny battery. All right, so the more positive one is the cathode. All right, the more negative one is the anode. All right, so which means you can actually calculate the E cell, and this E cell is can be calculated using E cathode minus E anode, which is 0.8 minus 0.34. That gives you a value of 0.46 volt, right? So that's only for one. All right, so over here, since there are 4 pairs in series, so you're going to say the voltage generated should be 0.46 times 4, right? Okay, how about the other 2? There are 2 pairs of copper zinc, right? Copper zinc is over here. So the more positive one is the cathode, right? This undergoes reduction. The more negative one is the anode, undergoes oxidation. All right, so what's E cell? E cell in this case would be, let me see, a 0.34, the E cathode minus the E anode, which is minus 0.76. Right, work it out, you should get 1.1 volt. So for these 2 pairs, it will be 1.1 times 2. So if you add up all together, right, you add up the E cell, right, for the total, I'm going to write down total, right? So you're going to use 0.46 times 4 plus 2 times 1.1. This will give you a value of 4.04 volt, right? So the answer for this will be C. Okay, let's look at the next question. Okay, use of the data booklet is relevant to this question by considering the relevant E values. Which halogen will oxidize Fe2 plus to Fe3 plus? So this Fe2 plus will be oxidized to Fe3 plus, right? Okay, so we're going to check the chlorine, bromine, and iodine on the left hand side. So we have to consider these 3, right? So we're going to calculate the E cell, right? The E cell has to be a positive value for the reaction to be able to take place, right? So this is definitely going to be the anode, and all the rest here will be the cathode. So you realize that E cell is actually E cathode minus E anode. So if it's only greater than 0, which means the reaction is feasible, right? So for this case, which one of them will be feasible? The E cathode must be greater than 0.77. Okay, so for example, if I use bromine, bromine will be 1.07 minus 0.77, and this will be greater than 0, which means the reaction can take place. So obviously you can see from here only chlorine and bromine will be feasible. All right, it will be able to oxidize Fe2 plus, since these 2 will give you a positive E cell. All right, so the answer will be A. Okay, the answer will definitely be A. Okay, let's move on. Next question. Okay, question 3. There's a galvanic cell which consists of magnesium 2 plus and magnesium, and copper 2 plus and copper. Okay, which of the following statements is correct? Okay, I've written down the half equation over here. All right. Okay, so the more positive one is the cathode, and the more negative one is the anode. Right, so you can see from here E cell is gonna be positive. Here is 0.34. Okay, minus 2.3. Right, so yeah. Okay, but anyway, let's look at which of the following statements should be correct. Okay, if you reduce the size of the magnesium electrode, magnesium actually electrode is the solid. So the thing is, if you change the size, you make it bigger or you make it smaller, all right, it actually doesn't affect the E anode, all right, because this is after a solid. It's like when you do Kc, when you do chemical equilibrium with the Kc, the solid is not part of the equation, correct? It's not part of the equilibrium equation, equilibrium constant equation, all right? So in this case, changing the size of the solid will not affect the position of equilibrium over here, right, for this magnesium, right? Which means so this is definitely wrong, because it will have no effect, right? No effect. So the answer is actually no effect. Okay, increasing the temperature has no effect on EMF. of the cell. Okay, if you increase the temperature, what happens is you can actually end up producing more aqueous ions. All right, so in this case, if I increase the temperature, there will be actually more aqueous ions, right? So equilibrium will shift, and that will actually affect the EMF. Okay, so I would say this is definitely wrong, because yeah, increasing temperature will create more ions. So for example, maybe increased temperature, there'll be more aqueous magnesium 2+ ions, so the E anode will be affected. So let's look at option C. We add sodium hydroxide to the copper half cell. All right, so what happens is you're going to form copper hydroxide precipitate. Okay, this is a solid, this is a PPT, and when that happens, the copper 2+ concentration will actually fall, right? Will actually fall, and this will actually favor the backward reaction. By LCP, it will favor the backward reaction to increase the concentration of copper 2+. And when that happens, when you favor oxidation, the electropotential value will always drop. All right, so when the electropotential of the E cathode actually decreases, what it means is E cell will also decrease. All right, so when they say increase, this is definitely wrong. Okay, so let's look at the last part. Okay, what happens when you, okay, let me remove this first. Okay, just take a bit of this. Okay, let me just write it all again. Okay, so let's look at the next one. So what happens when you add water to this magnesium 2+ half cell? In fact, when you add water, this concentration will actually decrease. So again, by Lachaze's principle, it will favor the backward reaction and you'll favor oxidation, and this will cause the E anode to actually decrease. So when E anode decreases, right, when E anode decreases, E cell will actually increase. So which means this is a correct statement. So the answer should be D. Okay, let's look at question 4. Okay, the use of data booklet is relevant to this question, right? The silver chloride silver reference electrode is based on the following reaction. So I've written this down. I'm going to call this the E anode, right? So I'm going to just, anyway, I'll just write this like that. Okay. Okay, so this value is the electropotential, is already with reference to the standard hydrogen electrode. I'm going to write it over here. Okay, so this is actually this is what you're supposed to find. They say what's the reduction potential of this electrode with respect to the standard hydrogen electrode, which is actually this value here. All right. Okay, let's read the question. They say the reduction potential of the iron 2+ iron half cell, which is this, is found to be minus 0.64 when measured against the silver chloride silver reference electrode. So this is your reference electrode. Okay, reference electrode, and sorry, electrode. Okay, and I want you to take note. Okay, right. Reference, and the right first, reference electrode. Okay, I want you to take note. The reference electrode is actually the anode. Okay, it's actually the anode. Okay, just take it as the reference electrode is the anode, because when we learn E cell, right? E cell is actually E cathode minus E anode, and this one is your reference. Okay, this is usually your reference. Okay, so they say the reduction potential was found to be minus 0.64 volt. Okay, this is a bit confusing, but actually what this value is, right, is telling you is actually your E cell. Okay, it's actually E cell, means it's found to be, means something like the voltmeter will read a value, the E cell over here will be minus 0.64. all right, when you measure it against the silver chloride silver electrode. All right, so which means we can actually try to apply the formula, right? E cell equals to E cathode minus E anode. All right, maybe I'll just write it one more time over here. So this is your E anode. So the other half cell, this is your E cathode. And the E cathode, we actually can find it from the data booklet, and this value is supposed to be minus 0.44. And the E cell is what the voltmeter reads, is minus 0.64. Are you me? And then you have the E anode, right, which is this silver chloride slash Ag. I'm just going to write this down. Here I should put all the standard condition, right? It's all standard. Yeah. Okay, so very quickly, you can actually calculate this then. So if you bring it across, you notice it's actually 0.64 minus 0.44. That gives you a value of 0.20. Okay, and that's the answer actually. All right. Okay, so I hope you get this idea about when they say something is the reference electrode. All right. Okay, just remember it's the anode. Okay, over here, let's look at next question. Electrochemical cell is set up using iron 2+ and iron half cell and a vanadium half cell. Okay, which of the following gives a correct effect on the E cell and a correct explanation? Means not just the effect on the E cell must be correct, the explanation must also be correct. Okay, so if you add KCN to this half cell, right, you add KCN to this half cell, essentially what it will form is this, and you must know that the Cn minus, right, the Cn minus is actually what I call ligand, which you actually will learn under transition metal. It will bind to the Fe 2+ to form FeCN6. All right, so this Cn is minus, there is 2+, so this is going to be 4 minus, right? So you're going to form this. So when you add Cn minus will bind to the Fe2+ to form this. So I can just safely say that this value will decrease. Okay, but at first you need to know that the more positive one is the cathode and the more negative one is the anode. All right, so when you add Cn minus, the Cn minus will bind to the Fe2+, and the Fe2+ concentration will definitely fall. So equilibrium wants to favor the backward reaction. Can you see that? Because according to LCP, and the E anode will actually decrease, right? The E anode will actually decrease. So when E anode decreases, right? When E anode decreases, E cell will increase. So which means this statement is actually correct. All right, this statement is also correct. So 1 is definitely correct. Okay, let's look at 2. Okay, adding water to the half cell. All right, adding water to the half cell, what happens to E cell? So over here you can see that when you add water, I want you to take note is you don't look at just on this one here. Okay, you don't look at this, because when you add water, in fact the concentration of this will fall, the concentration of this will fall, and the concentration of this will fall. So the concentration of all the aqueous ions will decrease, right? The concentration of all the aqueous ions will decrease. Okay, when that happens, by Le Chazelle's principle, it wants to increase the concentration of the aqueous ions. So you can see on this side, here, there are actually 3 ions, and this side there's only 1 ion. Okay, only 1 ion. So when all the concentration aqueous ions decreases, it wants to shift to the left. It wants to favor the backward reaction, okay, so that to favor the oxidation reaction, so that it can increase the number of aqueous ions. And when that happens, E cathode will actually decrease. So when E cathode decrease, in fact, E cell will actually decrease also. So this statement is actually correct, but actually this statement is wrong. Okay, so the explanation is because the concentration of the aqueous ions decreases. All right, so by LCP, all right, it wants to favor the production of more aqueous ions. All right, by LCP, so the position of equilibrium will favor the oxidation, will favor oxidation, means it will favor the backward reaction, okay, because that will produce more aqueous ions, and that will cause E cathode to decrease, and then E cell to actually also decrease. But the idea is not because of concentration of water increases, but because concentration of aqueous ion decreases. All right, okay, next one, increase the temperature of this half cell. So increasing the temperature will always cause the production of more aqueous ions. It's like trying to cause it to break the bonds, right, the metallic bonds, and you can get more aqueous ions. So increased temperature, all right, in fact I believe it will favor, yeah, it will cause the production of more Fe2+, and the E anode will definitely change. All right, so when they say no change, this is actually wrong. Okay, so the answer is actually A only. Okay, so let's look at question 6. Okay, I've written down all the half equations that you should actually consider looking at. Okay, so the colors of vanadium containing ions are given. What is the final color of the solution when excess aqueous hydrochloric acid is added? So some of you might be thinking of adding, looking at the H+, and some of you might be thinking of looking at the Cl-. Okay, let's look at the vanadium. Okay, vanadium, there are 2 parts to it. There's over here and here. Can you see that? So if I chose Cl-, Okay, I must always choose the ions on opposite side. So if I chose Cl minus over here, I must choose vanadium 2 plus over here. So what is my E cell then? Okay, what's my E cell? Can you see my E cell? My E cell would be, this will be my cathode, and this will be my anode. Can you see that? Because this one has to undergo reduction, and this must undergo oxidation. So it will look like minus 1.2, minus 1.36. All right. And this is definitely less than 0, which means it's not feasible. Okay, the reaction is not feasible. Okay, what if I chose vanadium 2 plus on this side? Okay, so if I chose vanadium 2 plus on this side, I would have chosen H plus on the other side. Okay, so you have to use the reactant on opposite side, right? So you must choose this one here. Okay, so what's my E cell? Let's calculate the E cell. E cell is equals to E cathode minus E anode, right? So this case would be this reduction and this oxidation, 0 minus 0.26. Yeah, this is definitely positive, right? Greater than 0, reaction is feasible. Alright, okay, but the question says you have excess, so you have excess H plus. So after producing V3 plus, okay, 2 plus become V3 plus, we can consider one more part, which is V3 plus and H plus. Okay, let's calculate my E cell now with V3 plus and H plus. You will realize that E cell will now be negative, right? So this one again will undergo oxidation, reduction, and this one must undergo oxidation. 0 minus 0.34 is negative, so there's no reaction. Hence, the final product is still just V3 plus. Okay, V3 plus. So that means it will be green. All right. Okay, let's look at the next question. Okay, let's look at question 7. All right. This is the cell diagram. So you must realize that this part is your salt bridge. Okay, I went through this in class before. This is my salt bridge, and the right hand side is reduction, is the cathode, and the left hand side is oxidation, and that's the anode. All right, that's the left hand side. Are you with me? Okay, so let's run through. So they gave you the half equation at the anode. So I'm going to write down the half equation at the cathode. So you can see that I have H plus, I have sulfate, and SO2 according to this. Right? So you can see the values. So the one that's more positive is the cathode, and the more negative one is the anode. Right? So this one should be the anode. Can you see that? So this should be the anode. So you can calculate your E cell first. So E cell is equals to E cathode minus E anode. So it should be 0.17 minus 1.63. That gives you a value of 1.80 volt. Right? Okay, so with that, you can calculate the Gibbs free energy. That's the formula, minus N F E cell. Alright, so I think all these are under standard condition. Okay, so N. Okay, what's N? N is the number of moles of electrons transferred. Alright, in this case, we take it to be 2. See 2 here? So, is that right? So, titanium will lose 2 electrons. Alright, and the 2 electrons will be accepted by the sulfate. Can you see that? So this N is 2, F is 96500, and E cell is actually 1.8 volt. Okay, work it out. Let's see what's the answer. I think you should get a value of minus 347,000 joules per mole. Alright, so you have to, after that, convert it to kilojoules per mole. So the answer would be D. Alright, so this is in kilojoules per mole, but yeah, when you use this formula, remember it's always in kilojoules per mole. Yeah. Okay. Okay, let's look at question 8. Okay, so there are 3 electrochemical cells set up as shown. The EMF or voltage of shown on each voltmeter. Okay, what you must remember is this. Okay, because this question is asking for the reducing agent, right? The order of reactivity of the metals. So the metals are usually on this side. Okay, metals are. So metals tend to be able to be oxidized, isn't it? If it's very reactive, means it can be very easily oxidized. So the more negative E value, right? If this E value is very negative, it means that the metal can be more easily oxidized, right? More easily oxidized. It is a stronger reducing agent. Okay, so we're going to look out for things like that. All right, so remember, the more negative the value, the metal is a stronger reducing agent because it's more easily oxidized. So I already drew a real number line here, and this real number line represents the electropotential. So the ones on the right hand side are the weaker reducing agents. The one on the left hand side are the stronger reducing agents because it's more negative, isn't it? Okay, so let's look at the table. Okay, for copper, the electrode, the plus is actually for galvanic cell. This is the cathode, and the minus is the anode. All right. So copper and metal X, right? So since copper is the cathode, it will have a larger electropotential. Okay, larger electropotential. The copper 2 plus, right? This is the one with the larger electropotential compared to metal X and X2 plus. Can? All right. So I'm going to say this for copper is somewhere here because I remember it's something like 0.34, right? 0.34 for the electropotential for the copper. So where is X? Okay, X is probably the anode, right? The anode always have the smaller electropotential because it has a smaller electropotential. So this is where X is. I'm just going to write down X. Okay, so this is copper and the side is X. Okay, so the next one, this is the cathode and this is the anode. But now the difference is actually 1.1. Okay, just now 0.5. So this is the difference here is 0.5. Okay. All right. So now the difference is actually 1.1, which means I believe metal Y should be somewhere here. Okay, because this gap now up to here is actually 1.1 volt. Can you see that? Okay, so metal Z and copper. So metal Z now is your cathode and copper is your anode. So which means metal Z would have a greater electropotential. So I'm going to draw Z over here. Right. So now they're asking you to rank from the weakest to the strongest reducing agent. You can see that the weakest is Z, followed by copper, followed by X, followed by Y. So that makes C the answer. All right, that makes C the answer. All right. Okay, let's look at the next question. Question 9. Which of following oxidations are theoretically possible under standard condition? So I've written down all the equations ready for you to compare, and you make sure they must always be on opposite sides. So let's check very quickly. So MnO4, this is like, I didn't write the full thing, but I guess you get the idea. So MnO4 minus and Cl minus. So this is your, okay, this is your cathode and this is your anode, right? This one has to be must be reduced, and this must be oxidized. And I always pick them on opposite side. Notice I always pick them opposite side. So E cell for this one will be positive. Cathode minus anode. This will be a positive value. So I'm going to put a tick here. So okay, let's look at the next one. Iron 2 ions and bromine. So bromine, I only have one possible equation to pick, yeah, from the data booklet. So this is the one. So I have to pick iron 2 plus on opposite side. Okay, so must pick on opposite side. So this one undergoes reduction and this one undergoes oxidation. This is my E cathode and this is my E anode. Right? So my E cathode minus my E anode will be positive. So I'm going to put a tick over here. So this is definitely feasible. Okay, hydrogen peroxide with dichromate. Okay, dichromate, there's only one equation you can pick, which is on the left hand side. So we have to, this will definitely undergo reduction. Okay, we have to pick the hydrogen peroxide on the right hand side. Okay, so you have to pick this one here. So this one will undergo oxidation. And definitely this is my E cathode and this is my E anode. So my E cathode minus my E anode again will be positive. So this is definitely possible. Okay, let's look at option number 4. So chromium 3 ions by iron. All right, chromium 3 ions by iron. Okay, if you notice something about this question, they say which of the following, maybe I should have highlighted this, the following oxidation reactions are theoretically possible. But if you look at the equation, you notice that this Cl minus, iron 2 and hydrogen peroxide, they are all being what? They are all being oxidized, isn't it? But when it comes to chromium 3 ions by iron, you realize that chromium 3 plus doesn't really become chromium like 4 plus or 5 plus. If you check your data booklet, okay, chromium is over here. So chromium 3 plus wants to be reduced and not being oxidized. Okay? So if you calculate E cell, you realize that this is actually feasible, but iron will actually reduce Fe3 plus, chromium 3 plus. It's not going to oxidize it. But because the question says oxidation, so we know that chromium 3 plus cannot be oxidized. It has to be reduced. So which means this is out, right? So that's why the answer is C, okay? So it's a bit tricky, yeah? So maybe you have to take note of this. Okay, let's look at the next question, question 10. Okay, the calomel electrode was extensively used as a reference electrode until it was replaced with the standard hydrogen electrode. Okay, so remember what I mentioned? I talked about the reference electrode was the anode. They say when measured with reference to the calomel electrode, the half cell containing zinc has a change in Gibbs free energy of that value. All right. Okay, so let's run through how this is done. Since they gave you the Gibbs free energy, you have to use this equation, right? Minus NFE cell. Correct? Okay, so we're gonna calculate what's an E cell, but since we have to change in G, the Gibbs free energy, and Gibbs free is in joules per mole, so I'm gonna write down 199 10 times 10 to the power 3. Okay, what is the number moles of electrons transferred? I believe since here is 2E and here is E, I'm going to multiply by 2. Okay, I'm going to multiply by 2, and I take it as the number moles of electron transferred is actually 2. Okay, and F is 96500, and then we can calculate my E cell. Right, this is a minus, of course. Okay, so what's E cell gonna be? Okay, let me check. Okay, E cell, if you did your calculation, it would be minus 1.03 volt. Okay, minus 1.03 volt. All right. Okay, so let's see the next part. Okay, so once you have the E cell, we can actually do the question. All right. They want the standard electrodes of the calomel electrode, and that's the reference electrode, right? So you can apply the formula E cell equals to E cathode minus E anode. So over here, this will be my, okay, over here, this one, right? This is my E cathode, and this is my E anode, okay? Because they mentioned that the calomel electrode was a reference electrode, and let it be the E anode, okay? So I'm going to just put in the value. So E cell is minus 1.03, right? E cathode is minus 0.76 minus E anode, okay, which is actually this one over here. Okay, so if you work it out, what's E anode? E anode is equals to 1.03 minus 0.76, and that will give you a value of plus 0.27, right? So that's the answer. Okay, that's why the answer is A, right? Okay, let's move on to the next question. Let's look at question 11. Okay, 11, they say use of data booklet is relevant. In fact, this question is linked to transition metals, right? So you notice all these are like transition metals, yeah? Okay, so which metal ion can be used as a suitable catalyst for this reaction? So we have to break this overall equation to two half equation, right? So I minus actually is going to react with S2O82 minus, okay? And you can calculate the E cell here. E cell here, actually, you think about it, this is oxidation, this is reduction, and E cell is 2.01 minus 0.54 is actually greater than 0. So this reaction is actually very feasible, okay? But they want which one of them can actually act as a catalyst. Okay, so how you do it is this. Okay, so if you pick copper 2 plus, so I'm going to choose. So this, you must understand that everything here in the aqueous form. So whatever catalyst we use must be what I call a homogeneous catalyst, right? All these ions, it must be in the same phase as the reactants, right? So since the reactants are all aqueous, the catalyst here, these homogeneous catalysts must also be in the aqueous form. So I've chosen this equation, and you can see that this is aqueous and this is aqueous also, right? So I didn't choose the one that gave you copper metal Cu, like Cu2 plus becomes Cu. I chose the one that becomes Cu plus, all right? So it must be, both sides must be aqueous, right? Okay, let's see how it works. So if I use copper 2 plus, okay, do with me, yeah? So if I use copper 2 plus as a catalyst, copper 2 plus will be actually reduced, all right? Copper 2 plus will be reduced. All right, and what happens is I minus will be oxidized. Okay, I minus will be oxidized. So you calculate your E cell, right? This is my E cathode. Alright, and you take this as an E anode. You'll notice that the E cell will be negative, which means the reaction cannot even take place. Alright, it cannot even react. So I'm going to say this is definitely 100% wrong. Okay, let's try the next one. Okay, let's try the next one. So if I use cobalt 3 plus, they asked for cobalt 2 plus. So if I use cobalt 2 plus, check. If I use cobalt 2 plus will actually react with S2O8 2 minus first. Right, so cobalt 2 plus will undergo oxidation and S2O8 will undergo reduction. Can you see that? And what is my E cell? Okay, this is my E cathode and this is my E anode, right? And the E cell, you realize that it will be positive, so that can take place, right? That can take place. And when that happens, okay, you're going to get cobalt 3 plus, all right? Once you get cobalt 3 plus. Okay, the cobalt 3 plus that is being formed is going to react further with I minus. Okay, it's going to react I minus. Can you see that? So what is really happening is something like this. So cobalt 2 plus, right, is actually reacting with S2O8. Okay, I'm not going to balance it, but I'll just give you the idea. It will react to give you cobalt 3 plus and SO4 2 minus, can? Alright. So after that, the cobalt 3 plus will then react with the I minus, and the I minus will become I2. Alright, and the cobalt 3 plus will go back to cobalt 2 plus. Alright, and then the cycle repeats itself. Okay, so when cobalt 3 plus we have I minus, right, what's the E cell? You calculate E cell. E cell should be 1 point. This one now will undergo what? Undergo reduction. So it's actually 1.89, the E cathode, minus 0.54. So this is actually positive. Okay, and the first one just now we did. Okay, it's actually the E cell for this one was actually 2.01 minus 1.89, which is also positive. Okay, so which means cobalt 2 plus is a suitable catalyst, right? So it's actually a suitable catalyst. Okay, so actually the trick is this. I said there's a trick to, or there's a shortcut to doing a question like that. So what you need to do is you take this equation, break it up into two half equation, as you can see from here, 1 and 2. Show the two half equation, which you actually can get from your data booklet. And how do you find out whether a catalyst is suitable or not? Alright, whether it can be a homogeneous catalyst. So the thing is, you just have to look out for one whereby the value like this, it must lie somewhere in between these two values. Okay, so if it does lie somewhere in between, it will definitely function as a catalyst. As you can see, we did calculation and it showed that it's actually possible. So if you're going to look at the next few, okay, look at this. This is 1.54, right, for manganese, right? Manganese 2 plus, right? So this is 1.54, and you notice 1.54 is actually somewhere in between, right? Can you see that? So which means this can actually also function as a catalyst. So if you look at V2 plus, okay, but make sure you pick those that are both equals, both on both sides are equals. So V2 plus and V3 plus, okay, V2 plus, V3 plus, and look at the value. This value doesn't lie somewhere in between, which means it's not going to work. All right, so the answer is going to be only 2 and 3. All right, so the answer is actually B. All right. Okay, let's look at the next question, 12. By using relevant E values, what are the vanadium containing products when chlorine is passed through a solution containing VO2 plus? Okay, so over here, I've already chosen over here. Okay, there's chlorine, right? Chlorine. So you pass chlorine through it. So chlorine will react with VO2 plus, and this one you must look for it on the right hand side. So if you go to the data booklet, you notice there are actually two of them here, here or here. And if you try to calculate your E cell, this is your, say for example, this is your E cathode, right? This must undergo reduction, and this must undergo oxidation, and this is the E anode. And you realize the E cell is actually positive, so it will work, right? So definitely you can get this, right? Definitely you can get this. At the same time, if you look at it carefully, this will also become this. Can you see that? So it's also feasible. In fact, both of them are 1 volt. So in fact, you will actually end up getting both of them. Okay, so but this question, they didn't tell you whether the medium is very acidic or alkaline. Maybe you can take note of this. Okay, both of them, the vanadium has a +5 oxidation state. Okay, but generally, if the medium is more acidic, let's look at my equation. There could be some equilibrium happening over here, which is not required in this question, all right? So if in a more acidic medium, all right, if more acidic medium, in fact, the equilibrium will shift more to the right, and you probably have more of this, right? So in an alkaline medium, you probably have more of this. Are you me? But since the question wasn't clear in this case, I'll take it as both of them should be present. So the answer is actually D. Right? Okay, let's look at 13. Okay, using of the data booklet is relevant to this question. Okay, you must be able to see that this is actually 4Na plus and FeCN6, all right, 4 minus. And over here, this is 3Na plus, and there's actually FeCN6, 3 minus, all right? So you actually have this and this. Alright, you have both of them over here. So the equation that you should be choosing is this one here. So one of the most common mistake is a student will probably try to choose this equation, which is not the case. So for iron 2 plus and iron 3 plus, take note there are 3 different equations. Normally we use this one if the medium is acidic. We normally use this one if the medium is basic. And for this one we use it in the presence of in presence of Cn minus ligands, right? Yeah. Okay, so this is what you learn under transition metals. So you have both of them. So I'm going to use this equation over here. This is the one that I have to use. So they say, which of the following can this be oxidized to this? All right, so this is going to be my E anode. So for any of them that is feasible, let's check. If you look at SO2, SO2 can only, okay, whatever you need, the other reagent that you need must be found on the left hand side. Okay, must be found on the left hand side. So this is out because it's on the same side as FeCN6, 4 minus, right? It's on the same side, which means is wrong. So how about NO2? NO2 is also found on the same side, so this is not possible. So the only option will be copper 2 plus and I2. So copper 2 plus, but if you use copper 2 plus, and this is my E cathode because undergo reduction, E cathode minus E anode will turn out to be negative, right? Which means this is also out. So all 3 of them are out. Let's try the last one, iodine. So iodine, if you chose iodine, this is my E cathode, all right? So my E cell will be E cathode minus E anode, which is 0.54 minus 0.36. Can you see that? With minus this, right? So this is greater than 0, which means the reaction is definitely feasible, right? So that's why the answer is D. Let's try question 14. Okay, so there are 2 half cells over here. You must be able to see that this half cell is made up of copper, chromium, not copper, chromium 2 plus and chromium 3 plus. Can you see that? Chromium 3 plus and chromium 2 plus. And the other half cell is made up of iron and iron 2 plus, which is the one that I've written down. So one of the common mistakes that students might make is they'll probably use this equation. Okay, they probably because this is they're more familiar with this, but this is definitely wrong. You can only use this equation if the solution has Fe3 plus and Fe2 plus and the electrode is platinum. Okay, but this case the electrode is iron, so you have to use the equation that I've written down over here. All right. Okay, so the more positive one will undergo reduction. So this is the more positive one. This is my E cathode and this is my E anode. Okay, so I'm going to write down here, this is E cathode and this is E anode. All right, and this is your E cell. Okay, this is my E cell over here. All right. Okay, so the only reason why it can go down to 0 is when E cathode must decrease or E anode must increase, because if this one decrease and this one increase, the E cell will become 0. Can you see that? Okay, so that's how it works. All right, so let's try. So what happens when you increase Fe2 plus concentration? What happens when you increase Fe2 plus concentration? So when Fe2 plus concentration increases, by Lachaze's principle, it will try to favor the forward reaction, because you put more Fe2 plus, it wants to shift to the right. Okay, it will favor the forward reaction, which means it favors reduction. So what happens for this first one is E anode will actually increase. Okay, E anode will increase. All right. Okay, how about the second one? When you decrease chromium 2+ concentration, so by Lachaze's principle, equilibrium will want to shift to the right, okay, to produce more chromium 2+. So favoring reduction, which means the E cathode must actually increase. Right. So last one, third one, chromium decrease chromium 3+ concentration. So what happens if you decrease chromium 3+ concentration? By Lachaze's principle, it will favor oxidation to produce more chromium 3+. All right. So the E cathode will decrease. Right, so the last next one, increasing the surface area of the ion. All right, so like what I mentioned just now, if you increase the size, the mass of the surface area of the ion electrode, it doesn't affect the electrode potential, okay, or the cell potential. Yeah, so this one, no, this is out. Okay, so this is out. So I told you which one result you have to look out for: E cathode decrease or E anode increase. So this gives me I only can choose 1 and 3. So the answer is going to be B. Alright. Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.